So 17.2% of all housing units are vacant. And then a supervisor wonders if her county is different from this. She randomly selects 907 housing units, finds 189 units are vacant. So without doing any statistics, let's just compare those real quick. 189 divided by 907. So that's about 0.21 for our sample proportion. So it looks like more homes are vacant in their area than in the census of 17.2%. Okay, and they're asking us to test just whether they're different. They didn't say explicitly to test whether their area is greater than 17.2%. They just ask us to test whether it's different. So when you're stating a null and alternative hypothesis, the alternative is the key. You want to make sure the alternative matches that statement that it's different. So this is the one that says different, not equal to. Okay. Okay, but the whole point of this is the null hypothesis is the no effect model, which means that nothing's really different from the average. Okay, we assume that nothing's different from the average, and then we say, well, okay, what's the probability that we got this number, 189 out of 907, assuming that the average amount of vacant homes is 17.2%. Okay, so under that assumption, we can calculate probabilities, and then we could say, hey, there's like a 2% chance that this is actually 17.2% in our area. So let's just reject that hypothesis and we'll say that there is some sort of difference. So that's the whole logic behind hypothesis testing. Which type of test is it? This is a proportion, right? When you calculate a percentage, you're calculating a proportion. And we don't have proportional t-tests. We get to use the z distribution because of some underlying theorems in statistics that if you have a proportion, then it's approximately normally distributed under certain conditions. So this is a one proportional z-test. And those conditions, I don't know if they're going to ask us in this question, but those oh yeah, it is right here. The success failure condition. We're supposed to do n times p sub 0 and n times q sub 0. So n times p sub 0 just means you take the hypothesized proportion and multiply that to your sample size of 907. And if that's greater than 10, then we're all set. Okay, that condition needs to be met if we're going to use that z distribution, if we're going to use the normal distribution. If that condition isn't met, then the probabilities we get from that table aren't going to really reflect reality. Okay, what's the difference between these three? Sample size is more than 100. That's not one of the conditions. It doesn't have to be more than 100 for a proportion. Okay, the condition is that we have to make sure we're sampling less than 10% of the population. So it's 907 home units. It depends on the area. For some areas like my area, that might be close to 70% of homes. But that needs to be a condition. 907 needs to be less than 10% of all the home units. There's no criteria like this that the standard deviation of p needs to be less than 0.5. So that's not a condition. That's not a condition either. That needs to be over 100. There's two big ones that you need to sample less than 10% of the population, and then we need these two conditions to be true. So n times p sub 0, did they tell us a decimal? Around to one decimal place is needed. So this is 156.0. And then n times q. Q is the complementary probability to p that makes it add up to 100%. In other words, take 100, subtract 17.2, that's the percentage for q. And then this is the decimal form, right? P and q are usually just written in decimal form. In this case, they gave us percentages. But remember, you always do math with the decimal form of a percentage. Okay, so 0.828 is our q. We multiply that to our sample size. 750, that rounds up to 751. Okay, unless I miscalculate something. Okay, so the conditions are met because these are both bigger than 10 and we've sampled less than 10% of the population. And we assume that they're random. You need to randomly sample them. And it is appropriate to use the normal model. We get to use that z-score. Okay, which sketch is correct? I guess I can't zoom out. Maybe I can do this. There we go. So remember what we said at the beginning. We're always assuming that this is true, that 17.2% is the amount of abandoned or unoccupied housing units. Okay, so this is the only one that has the distribution centered at our assumption. Okay, So we're assuming that this is true, and then we're going to calculate the probability that we got this number, assuming that it's true. So your distribution needs to be centered at the hypothesized population value, not the sample value. The test statistics, so I guess we're ready to go do that. The test statistic Z is your sample proportion minus the population proportion divided by the square root of P times 1 minus P. By the way, this is Q. Okay, that's just Q. Let me divide by N. So this is just plugging in the numbers that we have up here. 907 is N. Our sample proportion, 189 divided by 907. I'll keep some decimals here. And 17.2. So there's our sample proportion subtracted by 0.172, the decimal form of the percentage. And then we're going to divide that by, this is P times 1 minus P. Then we divide that by the sample size. So let's do that with our calculator. 1 minus P, that's our Q. We multiply that to P. Then you divide that by the sample size. And then I forgot this in another video earlier. You take a square root. And so this is the entire denominator once I plug those numbers in. Almost done the test statistic. So 0.208379 subtracted by 0.172, then divided by the test statistic. That's 2.9032 if we round to the nearest decimal there at the end. So 2 decimal places, I'm going to cut it off there. And then they want a p-value. You could just Google search z-score to p-value calculator. Yours is two-tailed. Just make sure you select two-tailed. Let me see if I can do it in StatCrunch. Get more help. StatCrunch. It's a calculator. You want to go to calculators, and we're doing a z-score calculator, which is the normal distribution. Okay, so what do we have? We had 2.9. We want standard, so 2.9. And look, this says a probability being less than 2.90. Let me see if I can get two-tailed on here. Doesn't look like I can. So I'm going to hit greater than in compute. Because look, here's like a z-score is always centered at 0. So 2.9 is way over here to the right. So this is the probability of being greater than 2.90. But that's why I emphasize that it's two-tailed, right? Because the hypothesized value, we said that it does not equal a certain, I think it does not equal 172. Okay, that means you have to calculate it for two tails. So that's a terrible normal distribution. But we just found the very small amount of area over here is 0.001865. You're going to have the same amount of area for your second tail that's on the left side. Okay, so if it's two-tailed, you've got to double a one-tail value. So I'm going to multiply that by 2. And that's our p-value. The p-value is the area in the tail. Oh, that's not my question, though. 3 decimal places. So if I round to 3 decimal places, I get 0.004. So the p-value is the area in the tails after you get your z-score. And that's a low p-value, right? If you have a low p-value, that means there's a low chance that the true percentage of vacant homes is 17.2%. So if the p-value is the probability that the null hypothesis is true and we get this certain value. So because the p-value is so low, there's evidence that there is a difference. We can reject that null hypothesis in favor of the alternative hypothesis. Okay? The probability that our local area has 17.2% of homes being vacant is roughly 0.004 based on our sample. That's a low probability. So let's reject that hypothesis. It looks like our county is different from the country as a whole.